If you were missing from class and you missed last class's lesson, you have to catch up. I do provide the recordings of the lessons on Google Classroom, but you have to catch up on any lesson you missed. This class moves fast. So we have a lot of ground to cover every day. In that first 10 minutes of class or 5 minutes of class that you get in, that's your time to kind of like take a mental breather. I understand some of you are taking very difficult curriculums, but you've got to stay focused for this one. And it's at the end of the day, but you've got to try to stay focused as much as possible. Because this is that class that if you're not paying attention, it's going to get hard real quick. And so today we are going to go over electron configuration, which is a topic for pre-ACE, and it won't be much more difficult than it was in pre-ACE. It should hopefully mainly be a review, but it is a large topic. It's actually a topic that if you saw it on the Cambridge exam, you would be happy to see. Most students would be very happy to see electron configurations as a topic on the Cambridge exam. But beforehand, let's go over the bell work. And because I don't have the wheel up, I will ask for volunteers. Take a look at this diagram and raise your hand if you can tell me what the charge on this plate is. Go ahead, Ben.
Positive.
Positive. And that's because electrons are negative and would be attracted to
Positive.
positive. All right, somebody else. Tell me the charge on the plate. Go ahead, Alex.
Negative.
Negative. Makes sense, right? Protons, which are positive, are attracted to a negative plate. How many marks have we earned?
1.
Right. Because it says here, complete the diagram with the relative charge of each. Each means you have to get both of them right for this 1 mark. So if you wrote positive, or you put a plus in there instead of the word positive, you wrote negative, or you put minus in there, you would get a mark if you got both of those 2 things correct. Let's take a look at the mark at the bottom. On the diagram, you are being asked to write an additional line. This line is to show how neutrons would behave instead of protons or electrons. Can anybody raise their hand and tell me what that does? Go ahead, Justin.
It's a straight line because it does have a charge
So straight line starting where?
from the source.
Correct. So you just do this, and you should make it clear. Oh, by the way, if you can't draw straight lines, like me, is there something that we would be able to use on a Cambridge exam that could help us with drawing straight lines?
Ruler.
You are always allowed and provided a ruler on a Cambridge exam, FYI. So you can't draw straight lines like me, and I can't draw them on these screens very well. But on paper, then you do have a ruler you'll always have. So you draw a straight line. And does it say to label it? No, but I would just to be clear. I believe as long as you draw a straight line, they would give you that mark.
Good question on the
This is a prior Cambridge exam question. This is a, which paper is this, by the way?
paper 2.
Paper 2. This is, I believe, from 2021, so not very long ago. And it was worth 2 marks. Paper 2 is worth a total of how many marks? Anybody know? Now we're doing like deep dive syllabus. 60 is correct. Paper 1 is 40. Paper 2 is 60. Paper 3? Paper 3 is 40 times 0.75. Whack. But what does that mean? Yes.
So why is it point top point?
There's 40 marks on a paper 3. But those marks don't weigh the same as the other marks. They weight them at 0.75, which means that every mark you earn on a paper 3 actually only goes 0.75 to your final score. Paper 3 is the lab paper, by the way. The lab paper is worth the least amount of marks. So,
Which one do you think is the hardest?
do I think it's the hardest? I don't. You know what? These days I don't know, because I would say traditionally paper 2 because you have to know things. Like you actually have to know things. With a multiple choice, you can kind of like be like, I got it 50-50. I can like at least get that 50-50 shot. And with the lab, you're going to get a ton of practice this year. And so I usually find that, the lab exams aren't too difficult. But last year, the students did really good on paper too. So I don't know what to tell you. They're about equivalent to me. Cambridge believes that paper 1 is the hardest, which is the multiple choice. But at this school, traditionally, the highest scores are on paper 1. So that's why I said it's very difficult to make that assessment, just because of what I've seen. All right, on that note, here we go. We are beginning. I am recording. There we go. So we are unit 1, lesson 2. This unit has only 4 lessons. After the end of the unit, you have a unit exam. So we're going to talk dates. Unit 1, lesson 2, electron arrangements in atoms and ions. This is a topic you may be familiar with, you may not be. It's called electron configuration. If you recall, 1s2, 2s2, etc., that's exactly what we're doing today. That's our goal for today's lesson. So if you don't remember it, then pay very careful attention because I'm going to teach it from scratch pretty much. Before we go over the learning objectives, and we will do that on a daily basis, I am updating you with some class dates. Now, I talked to Ms. Sauerowitz because I am under the understanding that there are several students in this class that are also in ACE Math. So we are doing our best to coordinate with each other that we don't give you exams on the exact same day, because that would be horrible, especially for those 2 classes. So what it's looking like is the following. Your final lesson is going to be at the end of next week for this unit, your final regular lesson. It's a short unit. There's only 4 lessons, which means hopefully it's the easiest test because it's got the least amount of lessons in it. That's going to be at the end of next week. There's going to be, for every unit, the way you're going to practice paper 1 is you're going to have a paper 1 quizzes. Now, for those of you who have had me as a teacher before, you know that I love quizzes. I pay the $100-something a year so that the students have access to it. I spent over 100 hours a few school years ago importing Cambridge chemistry questions, paper 1 questions into units so that you could have this resource. So I created this basically. You have a quizzes that's just on this unit, paper 1 practice questions from old Cambridge exams. And that's going to be due on Tuesday, 09/06. I tried not to put it on the weekend of Labor Day and give like an extra day, but you also have that weekend to work through it. It's going to be the way that I do the quizzes is on a Cambridge curve, meaning that if you get 85% of the questions correct within 2 tries, by the way, you get 2 tries at an 85. You get an 85, I put 100% in the grade book. And then it goes down from there. Like if you get between a 70 and an 84, it goes in as an 85 in the grade book. And that is the quizzes grade in this class, is the paper 1 questions you take on quizzes. That's how you get your grade for quizzes in this class. So actual quizzes aren't going to take place in class, it's just your practice on paper 1 is what I call your quizzes. There'll be maybe 1 or 2 actual in-class quizzes this entire year. I don't usually do much quizzes, I only do the unit exams. This has been highly successful for students in the class to get the practice on paper 1, so I'm continuing doing it. What I do each year is I just modify and add some additional questions and take some questions out as the curriculum questions update. So once again, this is going to post, by the way, early next week. Next class period, I'm going to post this. So I'm not giving this assignment yet. It's posting next class period. I always give a week to complete it. So you have a week to go through and do the paper 1 questions. What does paper 1 mean?
Multiple choice.
All these questions are multiple choice. And so it's an assignment, but it's a quiz. This is important. There are no late submissions allowed. Whereas I accept late submissions on other homeworks, I do not accept late submissions on the paper 1 quizzes. I have a very good reason for this, and I'm going to tell you exactly why. I have a buffer day in between when it's due and when your test is. On Wednesday, I'm going to release all the answers. So you get all the answers to study off of on Wednesday. I send them to you. So therefore, you have to be done on Tuesday night. I give you a week. So there is no late work on this. So have it ready, put a star on it. I will remind you next class that I'll be posting it right after next class. You should not do the quizzes that make sense? Because if we didn't do a lesson yet, you're going to get a question, you're going to be like, what's that? We didn't cover that lesson yet. So, and the way that quizzes works is the questions are shuffled. So you never know which question you're going to get first. And so it's best to begin it after we finish the last lesson, which will be next week, Thursday, I believe. All right. And then finally, your Unit 1 exam is going to be on Thursday, 0908. It's going to be the first half of class. So you come in Thursday, 0908. The first half of class is going to be a test. The test is going to be about probably 30 marks. 30 marks means 30 points to earn on that test. And it'll be on all the topics we've discussed already and what we have yet to discuss between the next 3 lessons. And so just so you're aware, that's what's going on. Tutoring dates next Wednesday and the Tuesday afterwards. So this should actually say 0906. Whatever that Tuesday is after Labor Day, that's when the exam review tutoring will be. And so I'll remind you closer to the time, but there's a tutoring session then. All right, finally, your practice packets, don't forget to turn those in at the end of the day today, unless you haven't been in school for a little while, then you have a little bit of extra time to next class to turn it in. But those do give you, not only is it an assignment grade, but I also am going to give you plus 10% on one of your unit exams for the quarter. So you want to start with that little boost just to make sure you're getting into the jive of what you need to do. So make sure you finish your practice packet. All right, here we go. So, learning objectives. This time, I just copied directly. I was working on adjusting this last night. And I copied this directly from the Cambridge syllabus. This is how it's printed in the Cambridge syllabus. So we'll go through this and we're going to do the same thing we did last time, which we're going to look at each of these standards, which are bulleted points, and we're going to see, do we remember this? Is this the thing we know? Or do we have no clue what this is? So, first off, and I wanted to include this because important information is in the Cambridge syllabus. It says, each atom or ion described will be in the ground state. Anybody know what that means? Go ahead.
The state is usually found it.
Right. So no excited electrons. I don't know if you remember electrons get excited. They can jump from low energy levels to high energy levels. That's how we saw different colors in flame tests. No excited electron energy states. Everything will be at the lowest level possible. So the electrons fill into the lowest energy levels. No, nothing strange, nothing out of the ordinary. And so the other thing it says here is they're only testing hydrogen through krypton. So on the Cambridge exam, you will only see electron configurations for the elements hydrogen to krypton, meaning they're not testing this topic past element 36. That's actually really nice for you because even in previous chemistry, I definitely tested past element 36. So that actually makes it kind of simple for the most part. I said that they're only going to test elements 1 through 36. That's all they're assessing. So this is why it's important to read the syllabus. Because when you read the syllabus, you know what's being required of you and you don't overstudy. So if you're going and trying and memorizing the electron configuration of uranium, I mean, good for you, but it's unnecessary for the Cambridge exam. Does that make sense? All right. Here are our objectives as they're listed in the syllabus. Understand the terms. Do you recognize what a shell is, what a subshell is, and what an orbital is? Put a check mark if you remember this. Put an X if you have no clue. You could be iffy on it as well. That's okay. We're going to re-describe it.
Electron configuration.
Yep. Principal quantum number. The letter N. Do you remember what that is? Or you're like, what? I defined it last year, but it might have went in one ear and out the other. That's fine. Just be truthful with yourself. Truthful with yourself so you know how much you have to go back and study. The ground state, which means not excited. Lowest energy possible. You remember what that is? Only limited to how it applies to electron configuration, yes or no? Next. Describe the number of orbitals making up sp and d subshells. This is actually something that's taught in previous as well. That I will reteach. You may not remember it, but you'll probably remember it once I reteach it. So maybe yes, maybe no. Do you remember the increasing energy of subshells? Do you remember? And so just to give you what they're actually saying here, do you remember that it goes 1s first, and then 2s, and then 2s comes before 2p, and then 2p comes before 3s? Do you remember that? That there is an order of increasing energy and what that is? They only, by the way, need you to go up to 4p. Where's 4p? 4. And if you recall, your periodic table breaks into segments. Where's 4p?
This side.
This side, 4 down. Well, what element is that? Which is what they said in the beginning. They're only going to assess up to proton, 36. So you only need to know electron configurations up to 4p, is basically what this means. You don't have to go into the F block at all. Describe the electron configurations. Well, maybe you do, maybe you don't remember it. Hopefully you will after I explain it. Explain electron configurations in terms of the energy of electrons and their repulsion. I will re-explain that as well. This is something we call Hund's rule back in the day. Electrons repel each other, so if they could, they prefer to be in different places. That's what that means. Determine the electron configuration of atoms and ions, given the atomic or proton number in the chart, using either the full electron configuration, which they give you an example here for iron, or the shorthand, which is using the nearest noble gas. If you recall this, you should put a check mark. If you have no clue, you're like, that's not a thing I know how to do. I didn't know that the first time we went over it, or I never even went over it. Do you remember the boxes? We didn't do the boxes. Do you remember them? Remember those who had the box? You just put a check if you know it, put an X if you're like, nope, gotta go back over that one clearly again. And then the final standard here is you're actually supposed to memorize the shape of an s orbital and the shape of a p orbital. Yes?
S, if we want to be the...
It's the dumbbell. Yeah, that's right. So if you know that off the top of your head that S is a sphere and P is a dumbbell, like that, then you put that check mark that you remember that. And if you're like, what you talking about? You put an X. So what you should recognize is that hopefully most of these are at least semi-familiar to you. And so much of what we do today will be a second look at something we've done before. If it's all new to you, maybe you need to rewatch the lesson, spend some extra time with it, because it is a pretty big topic. If I recall, in pre-ACE, we probably spend about 3 days going over a topic. We'll go over 1 day in ACE. That is the difference in ACE. So here we go. Beginning at the beginning. What we're learning today versus what we learned last class. What we learned last class, just to know what to go back to, is we learned atomic structure. We learned that protons and neutrons are in the nucleus, where all the mass is, and that electrons are on the outside of the nucleus. Today, what we're going to be learning, or relearning, is where are the electrons? How many electrons are in each energy level? That's what we're going to work on. So outside of the nucleus, we know we have the electron cloud, and that electron cloud holds electrons. Where are they? How many are there? And then that leads into how do chemicals bond with each other. It has to do with the electron location. So that's why it's important to discuss. So you need to know that electrons are arranged in what we call energy levels. If you'll recall in the Bohr model, these energy levels we described as little rings that went around the nucleus, where the first ring was energy level 1, which we would call n equals 1. If you want to fill that in, just to remind yourself, this is the first energy level, this is the second energy level, and then if you had more electrons that filled past the second energy level, you would go to the third energy level. And so the lowest energy level is energy level 1. That's the one that's closest to the nucleus. Electrons, do they want to be as close to or as far away from the nucleus as possible? What do you think? Close. Electrons want to be close. Yes. To be as close to the nucleus as possible. Because The nucleus is positively charged, and the electrons are negatively charged. But here's the deal. Electrons also repel each other. So you can't have too many in the same space. They repel each other. So you can only have limited amounts in different areas. And we're going to discuss what those amounts are. So far, so good? So the energy levels are also called the principal quantum number. That's a fancy name for the energy level. So if I say principal quantum number 4, that means that our electrons are in energy level 4. So you may just want to write, oh, okay, so energy levels equal principal quantum number. They are indeed the same exact thing. Cambridge wants to use fancy wording. They will say principal quantum number. In this class, we don't go over quantum numbers. Interestingly enough, if you were to take AP instead, you would see sets of numbers like 1, 0, 0, 1 half. Those are the quantum numbers. For us, it's kind of irrelevant because it's not part of the standards. So it's interesting that they even ask you to know what a principal quantum number is. But for all purposes, once again, when I see n or I see principal quantum number, it's just telling me the energy level, which is how far away or how much energy the electrons have. Those tend to correlate with each other. Energy level 1 is the lowest energy. If I have energy level 7, what would that mean? If I have electrons in energy level 7, would that mean low energy or high energy? High energy. And if you look at energy level 7, look at francium, look at radium. What do we know about those elements? Are they high energy? Well, they're radioactive. They don't stay together very long, right? Fall apart.
And one is French.
What?
And one is French.
Well, discovered in France. That is the biggest, random fun fact, biggest atomic size, francium. Part of our periodic trends when we get there. All right, so how do we fill electrons? First, we're going to look at simple electron arrangements, which is simpler than Cambridge will ask, but you need to understand the simple version of electron arrangements before you understand the more complicated one. First thing you need to know, electrons will always be located within the energy levels. There is no in between an energy level. And electrons either in energy level 1 or 2 or 3. There's no 1.5. Second, and this is really important, you always fill the lowest energy levels first, because electrons fill closest to the nucleus first, and then you build out from there. And then the third one, only a certain amount of electrons are allowed in each energy level. And these specifics we have got to remember. And you may remember it once we go back over it. Do you remember how many electrons are held in energy level 1? Yep. Do you remember how many electrons are held in energy level 2? It's actually 8. I'll go back over why, but it is 8. Energy level 3 starts to get tricky. Do you remember? Oh, close. Energy level 3 has 18. Let's see if we recall why.
Oh.
In energy level 1, we have what's called the S sublevel, and this only holds S. Energy level 2 has an S sublevel and it has a P sublevel. Energy level 3 has S and P and D. We're going to go back over these sublevels shortly, but this is the reason. If you recall electron configurations, S maxes out at 2, P maxes out at 6. That's the 6 you were all thinking of, by the way. And D maxes out at 10. And that's 2. 2 plus 6 is 8. 2 plus 6 plus 10 is 18. Now, if you recall, we can use the periodic table to come up with this because you should have diagrammed the periodic table at some time. And if you didn't, then you'll want to. The S section, the P section, the D section and the F section, which we're going to ignore F, but it is a section of the periodic table. And that actually describes how many groups is how many electrons it could hold in that section. And so we'll go back over that in a little bit, but you should write this down for now. Energy level 1 holds 2 electrons. Energy level 2 holds 8 electrons. Energy level 3 holds 18 electrons. Remember, we only need to go up to energy level 4, but I don't want to trap you there because technically 4 has an F group and we're not testing F. So we'll talk about that in a little bit. So, next. Electrons that are located in the energy levels that are further away from the nucleus have more energy. But it's weird, and we're going to spend a whole nother lesson talking about this. They're actually easier to remove than electrons that are closer to the nucleus. Why would that be so? If I've got an electron that's right next to the nucleus, whereas I've got an electron that's farther away from the nucleus, this is stating that the electron that's farther away from the nucleus is easier to remove. Does that make sense to you? So it's not being held tightly by the nucleus. Got a weaker force. So if something else came along that had a stronger pull, it would actually be able to steal that electron. So electrons that are farthermost, in the farthermost energy levels, are actually much easier to pull than electrons that are right close to the nucleus. We have a fancy term for this. We're going to learn next class period. It's called ionization energy. You either remember it or you don't. We have a whole class period dedicated to it. But that is how much energy is required to remove an electron. What you need to understand right now is that electrons that are close to the nucleus are held tightly. Electrons that are far away from the nucleus are held more loosely, but they inherently have a lot of energy because they're not stable. The electrons that are farther away from the nucleus are not as close to where they want to be, so they're not as stable. They are considered higher energy. All right. These are your basic electron arrangements, your Bohr model basic electron arrangements. This type of electron arrangement will not be asked on the Cambridge exam, but it gives you an idea for the energy levels, how many electrons fill into each energy level. If we look at an element like carbon, identify C on your periodic table. Noting what we have stated in the prior slide here, how many electrons would fit in energy level 1 for carbon? How many? Only 2, right? It can only hold 2. How many electrons does carbon have in total?
6.
6. So I'm going to write a little 6 here just to remind myself that carbon holds 6, has 6, but it can only put 2 in the first ring. So then, how many are left to put? 4. How many electrons could fit in the second ring, in the second energy level? 8. So can 4 fit in there?
Yeah.
So the simple electron arrangement for carbon would be 2, 4. And what that means is that for carbon, there should be 2 electrons in the first energy level and 4 electrons in the second energy level. This is just to help give you a picture of how electrons fill into an atom. They fill me outside of the nucleus into the energy levels, and there are specific amounts in each variable. This is not how it's asked on a Cambridge exam, just to give you an idea of how it works. We will have, and you'll see if you flip through the notes always, you'll see there's practice Cambridge questions later on in the level. All right, here we go. Sublevels. Do you remember sublevels? S, P, D, and F. So just to bring up what that is. Within an energy level is what we call a sublevel. This is where we're at right now. A sublevel is basically a section of that energy level. And so there are 4 different types of sublevels that electrons can fit into. Those types are called S, and F. And there's a few things that make them different from each other. One is their shape. They have different shapes. And they have different energies. Second is the amount of electrons that could be held in each one. And so within the sublevels, you have orbitals. You may want to write this out because this is the order of how it works. And in your orbitals is contained what? The electrons are in the orbitals. So right now we're looking at sublevels or subshells. Those are the same thing, by the way, sublevels and subshells. S, P, D, and F. One thing of note here that's in bold that you absolutely have to know, S is the lowest energy type. F is the highest energy type. F, I said, wasn't going to be tested, but I do bring it up because it exists. Like, it exists and I don't want to completely ignore it, but these are the ones that were tested, S, P, and D. So why does the S have the lowest energy and the F has the highest energy? I don't know if anybody remembers this. Let's go over them and we'll see why. This is S, right? Take a look at it. S is shaped like a sphere. So when we're looking at this, this actually goes into what's called the electron cloud model. In the electron cloud model, it's different than the Bohr model. The Bohr model is where you've got these rings, and these rings have these electrons. The electron cloud model is actually much more accurate. It basically states that there's probabilities of finding electrons somewhere in the area. And so you will not have to calculate probabilities. You will not have to do any math with this. However, you do need to understand that if you have a 1s orbital, that means that in this area of space, you can find how many electrons? 2. So there are 2 electrons flying around here. Like they're moving randomly and rapidly somewhere in that area of space, in the 1s orbital. What's the difference you can see here between the 1s and the 3s orbital? The size. The 1s is much smaller because it's closer to the nucleus. The 3s is larger. It's farther away from the nucleus. What's the same in 1s, 2s, and 3s? What looks the same in all the s orbitals? They all have the same shape. So every time you see S, it has a spherical shape. It contains 1 orbital. This may be something, I'll write it down. Every time you have an orbital, it can hold 2 electrons. So the difference between your S, P, D, and F is actually the shape and how many orbitals they hold. So S, if you'll recall, is 1 orbital. Always. Which means every time you have electrons filling into the S sublevel, it holds up to 2 electrons only. So it only holds 2. 1 orbital holds 2 electrons. What about P? Do you remember P? How many orbitals are in P?
4.
6 electrons. How many orbitals? 6 electrons means 3 orbitals. And the only other one you've got to know for this class is D. D holds 5 orbitals. So there's actually a distinct pattern.
And the other is 7 orbitals.
It's, yeah, 1, 3, 5, 7. And theoretical G would be 9. Like there's no elements we've made that have G. But if we did get that far, it would have 9. This is all Cambridge needs to know. S1, P3, D5. So each orbital is an area of space that can hold electrons. And these areas of space actually overlap each other, which is why when you look at the electron cloud, it's just like a fuzzy mess. Because you have a bunch of areas of space that overlap each other. You should memorize this definition. The atomic orbital itself is an area of space where electrons are on. So it's some area where you can find electrons. We call that an orbital. Yes? Go ahead, grab your orange pass though. Right. Kind of jogging, ringing a bell for some of you. Like some of this sounds familiar, perhaps, mayhaps. Yep, first quarter. So such an ace. P section. There are 3 orbitals. This is 2px, 2py, 2pc. Each of these 3 orbitals represents an area of space where you can find electrons. And so in each orbital you can hold 2. So if there are 3 orbitals in the p section, how many total electrons can be held? So every time you see P, it's always a set of 3 orbitals. So it holds up to 6 electrons. Every time you have it holds up to 6. Do you have to memorize the shape of P? You have to memorize the shape of S, and you have to memorize the shape of P. P kind of looks like a peanut, or like it looks a little bit like a peanut. 2 balloons 180 degrees from each other. Yes.
So are electrons flying around a blue area?
Right. So anywhere in this blue area you can find 2 electrons, except for one place. This is a good question. This right here, right there in the middle, you see at 0, 0, 0. It's called a node. Oh, what is that? It's not tested by Cambridge, but it's for your information. What does a node mean? It's actually a place. It's kind of, it's not a vacuum, but it's kind of like that idea. It's a place where you absolutely will not find an electron. A place where, like a dead zone, where you won't find an electron. The reason why this matters, the more nodes that your orbital has, the higher energy it has, the more complex it is. So let's do a little thing. I'm going to go ahead and I'm going to keep my ink annotations, and let's take a look at Google for a second. Because there's a good teachable moment in here. I'm going to go to Professor Google. Professor Google can be correct. Always verify. F orbital shape. This is the F block of your periodic table. These are the orbitals that each hold 2 electrons. Let's see where they go. Here's my F. First of all, for those of you that know, you know that S is down here, right? Like your uranium and your plutonium and stuff like that. Does that look complicated, first of all? Yeah, it looks really complicated. There's what we call a lot of nodes here. There's a lot of areas, there's a lot of splits. Basically, a lot of areas of space where you can't find an electron. The more nodes, the more complicated, the higher the energy. So that actually proves what I said earlier. S is the least complicated because it's literally just like this. No nodes, least energy, everything's just like flying around the space. For P, you basically take S and you squish it, like in the middle. Like, to understand the difference between S and P, this is S, right? Squish it. Now you have P, 1 node. 1 area where electrons can't go through, like go into. It gets more complicated after that. S to P to D to F. And then you get that crazy thing. Look at that, that's like 2 donuts. They're intrinsically connected, yes. It's very, very high level math outside the scope of this class.
F2, 3 is kind of like it's like a P, but 2 surrounding it.
Yeah, exactly. With 2 donuts. Like what looks like circular donuts surrounding it. Anyways, that's just to, because that's a really good question. So I wanted to entertain it. When you see this area of space here, it basically means that's a place where you can't hold an electron. So you can hold an electron here, you can hold an electron there, still a maximum of 2. Looking at that crazy F that I showed you, that crazy area can still only hold 2 electrons. So in those crazy like nodes, eventually lowest energy state. So electrons always fill into the lowest energy possible. So S will always get filled first in an energy level for that reason. All right, let's talk D. You do not need to memorize these shapes. Do not memorize. So just to be clear, this is not in standard to memorize these shapes. This is just me showing you what D looks like. The D sublevel comes in a set of 5 orbitals. These are the 5. Note that it's got more complicated. The general shape overall is usually like they call it a 4-leaf clover, but there is one that has a donut. It looks like, and you can see this is math. X squared minus y squared, yz, xz, xy, what axes the nodes that the actual areas fall on. But you don't have to memorize any of this. All you have to know is that somewhere in here, there are how many electrons? 2. Even though there's 4 areas here, there's 2 electrons somewhere in there. How did they come up with this, by the way? You know those physicists from back in the day in the early 1900s? They're called like Schrodinger and Bohr and even like Oppenheimer and Einstein. They all came up with these complex equations. They used physics and calculus, and they derived all of this, and it was proven later experimentally. And so it looks crazy complicated. But once again, you would not have to really understand any of this until a study in physical chemistry, which is a 3rd-year college-level chemistry course, which is outside the scope of anything you would do at CID. Anyways, so, and only a chemistry major would take a class, or a physics major would take a class that involves this. Anyways, so what you need to know is that the D section comes in a set of 5 orbitals. Each of those orbitals holds 2 electrons. So how many electrons can be held in this set of D orbitals? Now, we don't write the shape of D. So how do we tell someone that electrons are in those specific orbitals? What do we do? Because we're not going to do this. How do we tell people? How do we communicate? There's 1 electron in each of these 3 orbitals. That's where we use the orbital notation, which is called the boxes. When you saw me write the boxes out, that's basically filling the electrons into their orbitals, which you'll see shortly. Next thing, this looks crazy. Don't memorize this as is, but this is called the off-ball principle. For Cambridge, you do not need to memorize this name, but you need to know the idea. What we're more concerned about is you knowing the idea. This chart right here tells you the order of electron filling, because it tells you the order of what energy levels in orbitals are lower energy and what orbitals and energy levels are higher energy. And so what you should see is 1s is the lowest energy level and the lowest energy sublevel. And so electrons fill into 1s first. There's 2 orders to look at here. You should recognize that S is lower energy than P, which is lower energy than D, which is lower energy than F, and I explained why because I told you about the nodes. Right? The more complicated it is, the higher energy. So this is the highest energy orbital, highest energy sublevel, and this is the low energy. But there's an overlapping trend you need to be familiar with. Energy level 1 is less than energy level 2, is less than energy level 3, is less than energy level 4, right? Because the closer the energy level is to the nucleus, the lower the energy. It turns out the differences in the energies between energy levels and the differences in the energies between the sublevels are not always exactly the same. And that's why this ends up looking very complicated. However, gratefully for everyone, the periodic table actually can give away the entire order of filling orbitals, if you know just a few pieces of information. And so we are going to review that shortly. But I just wanted to bring up here that you'll notice that the order is here, 1s, 2s, 2p, 3s, 3p, but then notice that 4s comes next. and go over it now. So there are 3 different methods you can use, and you're going to pick your favorite one. It technically doesn't matter which one you use to fill sublevels and orbitals to get something called an electron configuration, which is how the electrons fill into sublevels and orbitals. First thing to remember is that electrons always fill in the lowest energy sublevel. The specific order of filling is the following. So if method 1 is just to memorize. Method 1, memorize. If you want to memorize, like I just have the time, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, if you just want to memorize that order, you'll always get the right answer. As long as you remember s is 2, p is 6, and b is 10. So that's method number 1. And remember, 4p is as far as you need to go for our AS level exam. We actually don't look past 36. We only go up to krypton. The second method, which I think is too complicated for what you have to do, is to use the off-bow diagram. And I believe I may have taught this at least to some of my classes last year, but the off-bow diagram, you basically list out all your possibilities. Energy level 1 has 1s, energy level 2 has 2s and 2p, energy level 3 has 3s, 3p, and 3d, and you go all the way down, and then you draw arrows. And it also gives you the order. 1s, 2s, 2p, 3s, 2p, 3d, 4s. Not my favorite method, but it exists. And if you don't have a periodic table, it always works. However, you do have a periodic table. Cambridge gives you a periodic table to use on your exam. So my preferred method, what I would encourage you to use to do electron configurations, is to use your periodic table to come up with that. So how does that work? And beforehand, let's answer a couple of checkups from the book. What are the 3 types of orbitals in the 3rd energy level? So types of orbitals means sublevels. So what is in the 3rd energy level? 4p, yeah. S, P, and P. That answers that. In S, 3s, how many electrons could be held? It asks for the maximum. S can only hold 2. Why don't I multiply it by the 3 in front? Because some students want to do that. Why isn't 3s 6 electrons? Just the distance, right? 3 is the energy level. It's not. So this is just a notation here. 3s indicates location, like how far from the nucleus it is, how much energy it holds. All right, 3p, how many electrons? 3d, how many electrons? 1 orbital in 3d holds how many electrons?
2.
Correct. Cambridge will do this to you on an exam. They'll tell you you'll have 1 3D orbital. How many electrons does it have? Well, 1 orbital only holds 2 electrons. So what's the reason D had 10 again? It's not because there's 5 orbitals. So be careful with the terminology. That's where it's tricky, is in the reading. All right. So just review real quick. This is 2, P is 6, and D is 10. Now, let's real quickly go through your periodic table, and then I'll go back to the other slides. But let's go to your periodic table. If you have a copy of your periodic table that I gave you or had the sub give you a couple classes ago, you may want to take that out. I have some extra copies here. If you need a copy of the Cambridge periodic table, please raise your hand, and I will get one for you. You need periodic table. I have a couple more, and I have to make more copies. Me? Okay, I'm out. table, in the section right here, these first two groups, you should do this. Put a box around it and call it S. This is what we call the S block of your periodic table. It is all of group 1 and group 2. You may recall this from pre-A. On the right-hand side, the other side of the periodic table, starting at group 13 and going to 18, put a box around that. We call this the P block. And for this class, you only need to know S, P, and D. So where's D? All these center elements, we also call them the transition elements, if you know. These right here. Call your D block. If you can remember, this section right here is S, this section right here is P, and this section right here is D. You can actually count the groups for an element to figure out where the electron configuration ends. So if I have, for example, silicon, what would be the ending of the electron configuration for silicon? Silicon's right here. Which section is it in? SP or D? P. Now the other part of it is, what energy level is silicon in? How do we figure that out? Does anybody remember? It's 3 because it goes like this. Energy level 1 is here. Energy level 2 is here. Energy level 3 is here. The period of the periodic table, which we call the row as well, is also the energy level. So silicon we know is in 3p. So far so good? How many electrons does it have in 3p? How would you figure that out?
How many electrons?
Count elements until you get there. So this is 1, 2. So we know that the end of the electron configuration for silicon is 3p2. How do we fill in the rest? So we know silicon ends at 3p2.
Use shorthand.
Yes. In the standard, if you look back at the learning objective, yes, you may use shorthand. What is shorthand?
It's the closest noble gas.
Beforehand. What's the nearest noble gas before silicon? It has to be before because it has to have less electrons. So we write neon in brackets. And so we've got neon and we've got silicon, but are we done or are we missing a part? Neon, we still have to count here. What area is this? So you have to write 3s.
2.
So for silicon, your answer is either, that's the shorthand, neon, and then 3s2, counting 1, 2 elements, and that's where you get the 2 from, 3p2, or you could have written 1s2, count your elements starting at hydrogen and helium, that's the beginning. 1s2, after 1s comes 2s. You basically read the periodic table like you're reading lines of a page. So line 1 is the first energy level, line 2 is the second. So you do 2s. How many elements are there?
2.
So you write 2s2. 2p. How many elements are there? 6. And then 3s2, 3p2. The numbers at the top here are electrons. So if you add all the numbers at the top, you should get how many electrons are in that element. So if you do the full electron configuration, you add all these numbers, they should add up to become 14, which is the amount of electrons for silicon. And that's one way you can prove you're correct. Yep. So on your periodic table, at this point, you should have diagrams S, P, and D. And we'll go back to this to do more examples shortly. There's something else you need to know. And you just got to know this. When you get to D, and remember, you're only going up to 4P, but you are going to get to D. actually not 4D, it's actually 3D. And this is because 3D has more energy than 4S. You have to subtract 1 from the group for the energy level. So it's subtract 1 from the period. Or D block. And it's always like that. And thankfully you don't have F, so you don't have to worry about it. But you do have to worry about D. So this actually gives you the whole order. 1S, 2S, 2P, 3S, 3P, 4S, 3D is the only strange thing you've got to remember, and then 4P. And that's how you can do any electron configuration for any element. 1 through 36 is what we need for this class. I'm going to get a little bit of time, and then we're going to go back a couple of slides because I skipped some stuff to get to the periodic table. If you understand this, this is the preferred method of doing electron configurations because once you get it, it's the easiest method. Yes?
What do you mean by subtract 1?
So if you look at D here, right? What number is that?
4.
But what is this actually?
Oh, okay.
So what I mean by that is whatever row you're in, you subtract 1 only when you're in the D block. Okay, so let's talk about this. Yes, I'm sorry. Question? Yeah, go ahead. When we are doing electron configurations, it is important to note that you are only going to be asked to do electron configurations in the ground state. Ground state means lowest energy state. There's also something called an excited state. If you put energy into an atom, you can excite electrons. We did this in the flame test lab. The different elements give off different colors, and that's from the electrons getting excited. You will actually see a flame test at some point later this year again, but you just need to know that you're only working with elements for this area for electron configuration that are at their lowest energy state, so they will always fill the way they're supposed to. S is always going to get 2, P is always going to get 6, so on and so forth. If you ever see something like an option choice that says 1s2, 2s2, 2p4, 3s1, does that look right? So you can actually automatically say, on a multiple choice, that ain't right. In order to get to 3s, that had to have been 2p, 6, right? So we automatically know on a multiple choice option that that can't be an option. That can't be an answer. Because you have to fill every section before moving to the next. Yes. Someone's out when they come back. All right. So I've already kind of showed what this is, but just to explain, when you're doing an electron configuration, you're always going to see 3 components. The number in front, which is the energy level you're currently in, a letter, which is the sublevel you're currently in. So this is all notation, right? Notation of energy area. And then the number up here is the amount of electrons in the sublevel. So 1s is your sublevel, and 2 is how many electrons are in that sublevel. You have to fill each sublevel completely before moving on. So going back to carbon, which has 6 electrons, can you prove, and do you understand using the periodic table why that is the electron configuration for carbon? Carbon's here. You start where? You start at 1, only has S. So you start at 1s2, then you read to the second line. What comes after 1s in order? 2s. And that fills at what number?
2.
So 1s2, 2s2. And then you move to 2p, and you stop at carbon because that's the element that's being asked about, so you end at 2p2. That's how you get that. That's the electron configuration for carbon. carbon. 1s2 twisted. So these are the three methods you can use to do electron configurations. You pick one and use it. I advise, this is my advice, is to pick the periodic table method. However, if you choose to memorize the alphabet diagram or you just memorize 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, whatever. Like, it'll work, it'll give you the correct answer, whatever works. But that's my preferred method, yes.
Helium is not part of P block, right?
Is not.
It's like kind of confusing, like right there.
Yep.
2s.
Well, it's the missing link here, right? To fill the 1s. That is the helium. Helium and hydrogen are all kinds of strange. But those first two elements are the 1s. They are both in S. All right, I already taught this, so we are going to look at some examples. Checked up means this is not Cambridge questions. This is, well, it's from the Cambridge textbook, but it's not a Cambridge examination question. We will look at those soon too. Use 1s2 notation to give the electron configurations. Be careful of the wording. If you are told that you have to give the complete, if it says complete electron configuration, that means you must start at 1s2. Another word for complete is full electron configuration. If they don't specify, you have to give the complete. What can you use instead? Shorthand. So you can use either if it doesn't specify that you have to use the full, but if they do say you have to use the full, then you do. And sometimes there's an incentive to using the full based on how they're asking the question. So let's take a look at this. Atomic number 4 is what element? So where do we begin? Filling. 1s. How many electrons are held in 1s? 2. Move on. After 1s, we go to 2s. How many electrons fit there? Are we done? Yeah. That's brilliant. 14 I already did. Like, done on prior tag. That was so. So let's look at 25. 25. What element are we looking for? I know. 25. It didn't say complete or full. So let's test the shorthand method. What is the noble gas that's right before manganese?
Argon.
Argon. So you would start by writing Ar in brackets, and that replaces those 18 electrons. Now do what? 4s2. And this is 3d. That's the trick you need to remember. D is always one less than the row of the periodic table. Yeah, you can go now. So manganese is 3d what?
5.
3d. So it's 4s2, 3d. 5. Remember that for D, the energy level is always one less than the row of the periodic table if you are using the periodic table method. 4s2, 3d, 5. 31. What element is that? Isn't that gallium? Are you okay with using shorthand here? Yes. Started argon. From there, where? This, right? 4s2. We go through the whole D section this time to get to the gallium, so it would be 3D, 10. Just count all the boxes. This goes up to 10. And then gallium is where?
P1.
4P1. Before I move on, valence electrons. What is a valence electron?
It's on the outer shell.
The outermost
Energy.
energy level, right? So just to classify, outermost energy level. It's gonna matter in a little while. That's why I'm asking it now. How many electrons in gallium are in the outermost energy level? The answer is actually 3. That makes sense. 4 is 2. 4 is the outermost energy level, agree? So there are 2 electrons, and then 1 more here. There are 3 valence electrons in gallium. Now, do you really have to look at the electron configuration to figure that out? Or you could just simply go, oh, well, gallium's right here, take the 1 off in the front, answer's 3 valence electrons. It's just proving it. That just proves it. We have tricks of the trait that we use, and I often use them with you in creating. But gallium has 3 valence electrons. This means that these 3d electrons, they're in a core energy level, which means they are not valence. You may want to point that out, because it's going to matter when we get to ions. Oh no. We have to do electron configuration if you look back at the learning objectives for atoms and for ions. So we did atoms, we've just done atoms, but what would we do for ions? Are we good? All right, noble gas notation. I've already went over this, however, just to be clear, to use the shorthand notation, you basically look for the last noble gas and replace its whole entire electron configuration with the element in brackets. You're basically like, I don't want to write all that argon. Instead of writing 1s2, 2s2, 2p6, 3s2, 3p6. And you start the electron configuration after argon. That's called the shorthand notation. You're allowed to use it for most questions. So, Tess, your turn, just to give you a little bit of time to try this yourself. Try this to yourself. Do the shorthand configuration for iron and selenium, and I'll check off on it when you have it. See if you can try these yourself. This is also your opportunity to ask questions if you need specific help or have a specific question for me. Yeah. You have it? Raise your hand once you think you have it, or if you have any questions. You got it. Good job. Great job. Ready? Anybody else I'm still waiting for? Raise your hand if you're ready for me to check. Great job. If you haven't yet done it yet, just raise your hand when you do have it done. Most people people have finished it at this point, so we are going to move on. Looks like overall you all have the idea. Yay. So we're going to move forward. This is actually a really quick question. I don't really see this type of question on the Cambridge exam, so I'd actually consider taking it out of the presentation, but I'm just going to leave it in. It's a really quick question. An element has the following electron configuration, blah, 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 5 is 2, 5p5. Which block of the periodic table would this element fall into? Yes, this is to check. Just don't put the commas. Take the commas out. And this is 3. Change the 40 to 3. Wait, here's this. So, the block of the periodic table that this element is in is what? P. You just look for the last part of the electron configuration, and that tells you the area of the periodic table that that element is in. So, P. Which group does it belong to? If it's 5p5. That means it's here, right? What group is this? Yeah, so you could say 17 or you could say halogens. Identify the elements. I do think this is easier than you did it, by the way. Okay. To check. So are you ready to see Cambridge questions? Okay, here it is, paper 2. And they were like, hey, we can test you up the krypton. Krypton. Electrons in atoms up to krypton 36 are distributed in sp and d orbitals. State the number of occupied orbitals in an isolated atom of krypton. How would you count how many orbitals krypton has? So this is actually kind of cruel because it's the last possible element that you can be tested on, and they're asking for you to count orbitals. So let's go ahead and walk through it. You would have to give the full electron configuration to figure this out, by the way. Shorthand will mess you up. What is the full electron configuration up to krypton? Start at the beginning. 1s, 2s, 2p, 3s, 3p. I got us to argon. 4s, 3d, and then 4p, 6. Okay. That's the electron configuration. Now the question is, for each type of orbital you have, type of orbital is the same thing as sublevel, by the way, or subshell. So for each type of sublevel, biletter, sp and d, how many orbitals are there? They're asking how many s orbitals have electrons in krypton. Can you count it? How many s orbitals? Well, there's one here, right? There's one here, there's one here, and there's one here. So if you came up with 4, that's correct. That's worth 1 mark. Does that make sense? So far? How many p orbitals have electrons? Go ahead.
9.
What's the correct answer? How did that come about? The 2p6 is sublevel. But every time you have p, it comes in a set of 3 orbitals, right? Because each of those orbitals holds 2 electrons. So this is actually a set of 3 orbitals. This is a set of 3 orbitals. And this is a set of 3 orbitals, which means that the answer here is right. But you get it? Does it make sense? With that explanation? calculations going on, that's fine. I'm pausing.
There's 3 sheets, so
Would it make more sense? Would it be easier for you if you envisioned it with the boxes, which we're going to do orbital notation in a little bit. But if you understood, when you see 3p or 2p, it actually is like this. And each of these boxes holds how many electrons? Like this. Right? 3 boxes, every set of p. Every box is an orbital. Anyway, D. We've got 3d10 here. How many orbitals? 5. Now, could you remember a trick to help you out with this? Knowing that one orbital is 2 electrons, you could literally just add up for P, for example, 6 plus 6 plus 6, which is 18, and divide that by 2, and that will give you the amount of orbitals. For D, you can take 10 divided by 2, and that'll give you 5. So there are quick ways around it. But that's the idea, is to count how many orbitals in total you have. And so this is the way that they took a question on an easy standard. This is actually a pretty considerably easy standard, and yet made it pretty much as difficult as they could possibly make it, based on the wording. And giving you the most complicated one they could give you. They were like, we're going to be rough. We're going to give them a rough question this time. 3 marks, 1 for each box. That's the way it works. If you see a 3 here and you see 3 answer choices, it's 1 for each. Now, this is the opposite. They're being extremely kind. So I would call this a level 2 question, like definitely not the most easy. And I always give a variety, by the way, on the unit tests and the quarterlies. I give a variety of questions to match that they give a variety of questions. So you won't only get hard questions and you won't only get easy questions. You'll get various levels. This is level 1. Meaning, this is about as easy as they can give you a question. Complete the diagram to show the number and energies of electrons in an isolated atom of silicon. They've given you the boxes. Just to recognize, the boxes represent orbitals. Interestingly enough, in all the questions I've seen reviewing old exams, they typically do give you this, which is nice. That they give you the boxes and you just have to fill them with electrons. It also gives you the orbital, because you go from low energy to high energy. So there's already 2 electrons filled here. For silicon, how many electrons would you put in the next box? 2. So I'm up to 4. And I need to get to 14. In 2p, how many would I put? 2 for each box. Just to be careful of your order, you do up, up, up first, and then down, down, down. What does that mean? When you fill, you should fill in this way. Up, 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 down, down, down. Does anybody remember why? Why do I fill 1 electron in each box before putting the second electron? It's because electrons repel each other. So at the same energy, they prefer to be in different spaces, different orbitals if possible. So you always fill 1 electron in each box first before putting 2 in any box. That had a fancy name. It was called Hund's rule. I don't need you to know the name of the rule, but I do want you to know the idea because it's part of the assessment here. 3s. How many electrons do I put there? So 2, 4, 6, 8, 10, 12. How many electrons do I put in 3p? And that's where one of the marks is at. So you do 3p, and you have to do it like this. The idea is that because electrons repel each other, one goes in each orbital first. And what I mean by that, 1 electron goes in each separate orbital of equal energy first. So you don't put 2 electrons in 1 orbital and leave the other ones completely empty. If they can separate into different orbitals, they do. And so this is the answer. Where are the 2 marks here? Where do you think they're at? Because that's something we just got to get comfortable with evaluating. 1 is for getting 14. If you filled 14 electrons into here, that's 1 mark. That's why I said it's a level 1 question, because that's about easy. They told you it's 14. Gave the boxes. And the second mark is where?
To like put it in this correct boxes.
For 3P, putting those two, 1 in each box. That's where the second mark is at. So that's what they would call the little bit harder mark, because you have to remember that idea in order to get it right. So 2 marks in total here. Bottom question. Diagram shows the orbital. Looks like that. How many electrons exist in all orbitals of this type in an atom of fluorine? Do we understand that question? What is this?
A few orbitals.
P, right? How many electrons are in p orbitals for fluorine? Can we figure that out pretty quickly? Fluorine's here, right? So it's only got this area. 1, 2, 3, 4, 5. The answer's 5. If you got 5, you got it correct. And so literally you get 1 mark for putting the number 5. No sentence. Please don't say, it is 5 because. Don't do it. That's what I was telling you earlier. In this class, say less. You only state what you need to state. Yes. That's fine. You're just repeating this word. They won't count that against you, but they don't care that you wrote it. Like, they're like, whatever. Sure.
You might say 5 orbitals instead of 5 electrons.
But if you say the wrong word, 5 ions, for example, it's definitely wrong now. So say less. Just put 5. I know that I tell you something different than probably a lot of your other teachers, but I'm telling you that is how it is for this exam. Alrighty. So I double checked. I looked through the textbook. I have not seen questions on this in many years, but when I looked through the new 2022 textbook, I looked last night just to make sure. It's still there, so I still have to teach this. There is a potential exception in electron configuration, one in which you need to be well aware of. And it's new for everybody. If you took pre-ACE last year or not, I did not teach this in pre-ACE. I don't think I did, at least. If you have copper or chromium, and it's only these 2 elements you need to be concerned about, a weird situation occurs. You would think, and I'm going to show you chromium. Chromium's electron configuration, you would think, what's before chromium? It's argon, right? You would think it would be argon, 4s2, 3d4. But that's actually wrong. That's not chromium's electron configuration. A little bit more investigation is necessary here. Write out the boxes. 4s. How many electrons do I put in there? Here. All right. Take a look at 3d. Comes in a set of how many boxes? How many orbitals? Boxes stand for orbitals. Comes in a set of 5. So 3d4. Go ahead and fill 4 electrons into 4 out of 5 of those boxes. 1, 2, 3. Now I haven't seen this tested for a while, but that means that it's possible to be tested soon. Because I don't know how much you know about Cambridge exams, but they like to wait a decent amount between testing topics sometimes and then bring back something that's really old. And so I did still see this in the textbook, so I am teaching it. I was going to take it out, but I double checked the textbook to make sure it was there. And the reason I was almost going to take it out is I haven't seen it in forever, like on a test. But here it is. Write this out for now. I'm telling you this is wrong. I'm about to explain to you why this is wrong for chromium, which is crazy because you're like, no, it's not. But it's actually been experimentally determined that this is wrong. We use theory to help us understand what we've seen experimentally. experimentally, we know this is wrong, and that it's something else. The something else is written up here, actually. This is the correct answer. But let me go back to something to explain it. We're going to go back all the way to this crazy diagram I showed you earlier. That one. Take a look at 3D and 4S. Does the energy difference look to be very different or pretty close?
Pretty close.
Pretty close, right? That energy difference between, and that's why they flipped actually, because it actually turned out that the difference between 3P and 3D was great enough that 4S got really close in there and it came in before, which is why the order is 4S 3D. So we got an issue here. These two are really close in energy, 4S and 3D. And you've got this. You've got this. I need you to pay attention. You've got an empty orbital here. Oh! You've got an empty orbital here. That electron doesn't like that other electron, does it? It's like, I'm repelling you, right? We are repellent to each other. But these two sublevels don't have very much different energy. So guess what happens? Because the energy difference is so small, and these two, you could use a strong word, you could say they hate each other. Right? So what does one of these electrons do? Like, bye. I'm moving over there. And so what happens, and it only happens with chromium and copper, is that one of the electrons jumps from 4S to 3D. So you want to write that, maybe write that out in words to help you out. One of the electrons.
How would you do one?
I'm going to explain why that works as well shortly. One of the electrons jumps from 4S to 3D only in chromium and copper. Only in those two elements. So if they were to test it, it's because they're being mean to you. If it shows up on a paper 1 or paper 2, they're like, oh, we're going to get them this year. We're going to give them the exception. Haven't seen it for a while, but I always teach it just in case. I double checked it was in the textbook still. Yes. Yes, you may. So, one of the electrons jumps from 4S to 3D only in those two elements, which actually means that the correct answer here for chromium is argon, 4S1, 3D5. And the reason for this, there's a reason. Half filled and completely filled. Half filled and completely filled. Subshells or sublevels are more stable. They're more energetically favorable. And so that means that at 3D5 and at 3D10, that's actually more favorable than having one away. So half filled and fully filled energy levels are actually more favorable for stability. Completely? CR and CU? CR and CU. CR and CU. To be clear. And this is because completely filled and half filled sublevels are more stable. So this happens with chromium. It also happens with copper. Those are the two. They're one away from 5 and one away from 10. Okay. So that's a great question. So would it happen with any of these others? The answer is yes, because elements in the same group behave the same way. So yes, the same exception happens down that group and down that group for most of those elements. Yes. Great question. But we only go to that area, so that's why we just say partial copper. Yes?
Do you have Manuela? Oh,
No?
did I just tell them?
This is bleach.
Yeah, sorry, down the wrong room. Sorry,
Okay,
sorry.
no problem. Like, I don't think so. If you ask one of my previous classes, I might not be quite sure yet because there's a lot of students in there and I'm still working on it. All right, so we've got one more thing to address before we're done for the day, and the topic is called ions, our good buddy ions. What about ions? You remember those? What's an ion? Atoms with charges, meaning that electrons have either been,
Or gain.
right, electrons have been gained, and that would be negative, or lost, which is positive. So you know you have an ion if you see a negative or a positive charge. So how does this have to do with their electron configuration? What would you do with the electron configuration if you had an ion? Well, there's good news and bad news. If it's a negative ion, life is pretty simple. First of all, most negative ions are made, like if it's made naturally, it'll go to its nearest noble gas. Like that's the whole idea of how things happen, right? We gain electrons to get to become like the nearest noble gas. So you probably just end in a P6, probably. But the idea is that if you see a 2- charge, that literally means add 2 electrons to the last sublevel. Right? So at the end, if I'm adding electrons, I can only add them at the end because everything else is full. So why do elements gain those electrons? I just said it, but why?
Becoming normal gas.
To become more stable, and often this is to become like the nearest noble gas. Often nearest noble gas. I say often because transition metals exist and they're a little bit more complicated. Welcome back. So ions. If it's a negatively charged ion, you just add however many electrons it says to the end. This will often give you a P6 ending and fill the energy level, which is what you see with S2-. Giving a little bit of time, and then we'll look at positive ions. Positive ions are the weird ones. Positive ions. Yes. It would be, no, it wouldn't transfer for iron. It literally only does it for chromium and copper when it's one away. Copper, it would be fill these 3, change that to Cu, and then fill those 3. So it would be 3 times. All right, what about positive ions? This is going to be strange. Let's take a look at zinc. And I'm going to give you the full electron configuration for zinc. Zinc. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. This is zinc. And just write it down. Notice I've left a lot of space here because I have a reason. Write strange or alert. This is something you're going to have to study to remind yourself, because if you don't review it, it's something many students get wrong. If an issue occurs, it's usually for positive ion. Question is, I want the electron configuration for Zn2+. Oh, by the way, and if you're new to taking classes with me, and even if you're not, you may have forgotten. Zinc is one of the elements you have to memorize. It has a standard charge when it forms an ion. There's a few. It's these 3. Zinc is +2. That's why I wrote +2. If you don't know that, it will come up later this year. But there's a reason it's +2. It actually has a standard charge. when zinc forms an ion, it forms a +2 charge. Actually makes a lot of sense. And I'll explain in a little bit. But where do those 2 electrons get taken from? If this is zinc's electron configuration, first question, would you take the electrons from the innermost energy level? The electrons that are right next to the nucleus. You're not getting to them. They're shielded. They're protected, right? Those electrons are protected by a lot of other electrons. So which electrons will you take? Which electrons get taken the easiest? The valence electrons. Absolutely correct. The 4th energy level. Wow, you all are so smart. These get taken away. Even though they were not written last. The deal is that electrons, and I did say this earlier in the class period when I showed you the Bohr model, I had a reason for doing that. When you go back here, you should recognize that there are only 2 valence electrons here and that everything else is in the 4 level, right? There's only 2 valence electrons here. These are the ones that get pulled off the easiest, get taken away first. Furthest energy level, highest energy level. So you take away from the 4s. How many do you take away for zinc 2+? 2. So it would be 4s because furthest from the nucleus. So the actual electron configuration for this would be, you literally just take that out. Goodbye, 4s. Those electrons are gone. So it would be whatever is left. 1s2, 2s2, 2p6, 3s2, 3p6, 3p10. Well, does it now make sense that zinc is always +2 because you take away its 2 valence electrons? That one actually does make a lot of sense because all you have here is inner energy levels now when you take away the 2 electrons for zinc.
What's the other ones?
It's a zinc, cadmium, and silver. Zinc, cadmium, and silver. Silver's always +1. Zinc and cadmium are always +2. Yes.
It takes the first 4s.
Yes.
The next one I will take.
Would be 3D. The next one it would take, if it took more, like if more than 2 electrons were lost.
Does that also work for manganese, iron?
Yes. Yes. Well, all transition metals, it's the same. You take away from the 4s first.
Is it also like that for 5s or is it for 4s?
Same for 5s to 4D, which is not tested, but it's the same idea. So, we take away electrons from the furthest energy level. If all the energy levels are, like let's say you had just ending 3s, 3p, 3d, then you take away from the highest energy. So it's furthest energy level first, and then it's highest energy after that. So now that you know that, we should be very close to the end now. There's a checkup here. See if you can try these, that I've shown you the one with zinc. Try these 3 and show it to me when you're done, and I will check you off on these. Let me double check. I think I might have one more Cambridge question to look at before we're done. Yeah, there's one more Cambridge question to look at. If you want to attempt that one as well, go ahead and I will sign off on both of them when you're done. The last 2 slides are practice questions. As you're working through these practice questions, I have your homework. I have your homework. The homework is due. Remember, it's the night before the next class. So this homework is based off of the first 2 lessons, which is atomic structure and electron configurations. I'm passing this out. Work on the rest of the questions, and when you have them, have me check them, and I'll let you know if you got it right, got it wrong, what you need to fix, if so. Put it in your notes, and I'm going to sign off, and this gives you credit for your notes. And I'm passing out homework. Homework is due next class.
Or
All right. If you have questions or if you're ready to have me check, raise your hand and I'm signing off on your notes. These last set of questions are for you to do. So these two are right, but this one's not. And the reason why is because you take away from the 4S before taking away from the 8. Three. And you're working on that one. Remember to raise your hand either if you're ready for me to check or if you have a question about the question. Okay. Is this the check? For this one, you have to take. I think you took away one too many because when you count up the numbers, you don't get 22. We started at 26 and it's 3 plus, so it should be 3 left. And then this one, it's a negative charge, so you have to add it. Yes, over here. For which one? We still have to do this one. But that's right.
Good afternoon, Golden Lions. This is Devin Grant, and these are your afternoon announcements.
Students, please remember to check your Cambridge email daily and report to your school in proper CIE uniform. Make sure your outerwear is solid white, black, or red and does not have large logos. If you are wearing Crocs, you must wear the back strap. Also, please wear your student ID badge around your neck at all times. Detentions will be issued to students who do not adhere to the uniform policy.
Please remember, students are not allowed on the second floor or in the stairwells during lunch. Also, eating in the hallways is not permitted.
Juniors and seniors that are currently 6 cars in the student parking lot that do not have the decal. Starting Monday, if you do not have a decal, your car will be towed.
Art and Gardening Club is hosting a Jeans Day next week on Friday. Remember, torn or ripped jeans are not allowed. Cost to participate is $1. You can pay as you enter the building. This concludes our afternoon announcements. Have a wonderful weekend, CIE.
Just kidding. It's Ms. Kaufman. You guys are doing a great job with your mobile devices, but if you have requested one and you haven't gotten one, it's because I have not received the email copy of your insurance purchase. Those of you who did the income verification instead, that is up on OSP for you to participate that way. I still have plenty of computers, so make sure your parents do the mobile device agreement, and you'll get one first thing Monday. Thank you, and have a wonderful week. We finished week 1, a full week 1. Have a good weekend.
Oh my God.
Don't forget your homework from last week. Turning it to the period it's been at the end of the class period. All right, have me sign off on it. If you're ready, remember I do need to sign off on your notes. This is correct. Excellent. Yeah. Great job.
But you get rid of the electrons before we get rid of
What? You didn't say the after how they talked last year?
I saw them like, you know, in April. I saw her binder, it was small, and she had it like this. So,
What do you think? It'll be cool. Because not only are you getting those, I'm giving you your tests back. So when you look at all the things you get, it just fills up over the years. So it's day 2 technically. You're done day 2. If you didn't get my signature, just show it to me at the beginning of next class during bell work. If you didn't get my signature. Is that okay or overwhelming or over okay? Okay, turn it on like it will. I'll look.
Let's go over lesson 2 and lesson 3.
Okay. Remember, if you didn't get both questions checked by me when the bell rings, have me check at the beginning of next class while you're working on bell work. That'll be the general process, okay? Why do I see 3-methyl-hexanoic acid? Is there like a thing there? On there? Where'd that come from? Like looking up 3-methyl-hexanoic acid? All right, everybody have a wonderful weekend. I will see you next week. Thank you for staying, making me awake. And getting your stuff
we can't
done.
leave until we. No, yeah.
I have a section here. What?
Yes, you did, David.
What? When? In what moment?
Attention teachers. There is some maintenance that's being done in the building. All teachers, everyone needs to leave the building by 3 o'clock.
Oh,
3
boy.
o'clock, everyone must exit the
They're
building.
kicking us out. They're like, goodbye. Hi. Go ahead, ask.
What class do you teach for 6?
This one is ACE, like the second year count. That's the one after the one. This like Ved was in the class with you. Hi. What?
I want to switch out of business.
Oh, to chemistry?
Yeah.
I'm down. I'm cool with it. But you would have to come to tutoring next week to kind of catch up on just the little topics that you missed, if you want to do it. Like
I'm thinking about it.
Yeah, just so you know, I would need you to come to tutoring so I could catch you up because we started on Wednesday with material, so I will have to catch you up if you switch. It's not like the end of the world. It's just like I'm letting you know. I'm happy to have you though. Our class is I think like 18 students, and so it's a pretty low student to teacher ratio, and I know you're good for it.
Too much.
Too much what?
Too much vocabulary.
Oh, you don't like the vocabulary?
No. I'd rather do like
Math?
yeah. So
Okay, it's up to you. But I would approve it if you ask for that schedule change.
do you know by when like the first schedule changes?
I don't know, but I do know you have to fill out a form still.
And they have that in the office.
Yeah, they have it in the office. Bye.
That's it.
Yeah, just consider it maybe today over the weekend. And like I said, if you do get in the class, I would need you to stay because I need to I need to catch you up. I mean, if it's a different date, you just let me know because I'm literally only doing tutoring for like that class right now, so I can stay late. I'm not doing anything for pre-ACE right now because their stuff is like. They learned about like lab safety, so I'm not doing tutoring yet because I don't need to tutor you in lab safety. But for this class, like we did structure of the atom, how to calculate protons, neutrons, and electrons, and we did electron configurations today, which was the 1s2, 2s2. So we have to go back over that just to make sure you're on the same page with everyone else.
I was set on taking ACE last year.
You were. You told me.
Environmental.
Did you pass?
Yeah.
Okay, cool.
Like I got stuck there, and then business.